Hello, welcome back to my channel, and in this video we're going to learn about wave function collapse, which is one of the favorite concepts everybody loves to learn. But in this video we're going to learn why do we have to include this in our theory, and the answer is to make our theory consistent. So let's rewind back what we did in our last video. In the last video, this was the question that was asked, where were the particle before you make the measurement, because our Schrödinger equation giving us a wave function, and from wave function we were able to get distribution. And so one of the questions you could ask, where was the particle before you make a measurement? And Einstein thought the theory is incomplete because it's not able to predict where was the particle. So he said there's some hidden information that we don't know. And then there was people who thought this is metaphysics because you're asking the information about before making the measurement, so it doesn't really matter. And John Bell came in and he came up with this Bell's theorem, said that the particle there was no hidden information that could make the theory complete, and it does matter where the particle was before you make a measurement. So you have to get rid of these two notions, and then the accepted notion was that the particle was nowhere and the measurement forced it to be there. So now, but with that interpretation of quantum mechanics, there's some contradictions coming, and let's talk about it and how do we solve it. So you have this probability wave function, you have this distribution, and you make a measurement and it come out to be at position A. So now one could ask a question, if you make a measurement right after the first measurement, where would the particle would be? The obvious answer is you will get a position A, because if you repeat an experiment, you should get the same result, and that was the notion. But if you think like that, this is in contradiction with the interpretation of quantum mechanics, where we said, because if you make the measurement right after the first measurement, you get the same position, then it seems to suggest that the particle was already there and continues to be there, which clashes with our idea that the particle was nowhere and before you make the measurement, and our measurement forced it to be there. So there is a contradiction between experimental results and our interpretation of quantum mechanics. The solution come out to be the wave function collapses. And what does that mean and how it solves this contradiction? Let's see that. Imagine you have this wave function and you make a measurement and it came out to be at position A. So what is this wave function collapse? Is that when you make the measurement, the wave function, your probability density function become very sharp. It changes this distribution and it peaked around A very sharply, and this is what known as wave function collapse. So when you make a second measurement, that's why you're getting the position A, because the wave function has collapsed. But you have to make a measurement very, very fast, because wave function does evolve after some time, because it has some distribution, it collapses, and it evolves again according to the Schrödinger equation. And you have to make a measurement quickly since it's spread out after the first measurement according to the Schrödinger equation. This seems to solve the contradiction that we had before, and if you make it fast enough, you will get position A, but if you make it after some time, you will get a different kind of answer, because now the wave function has evolved it's not the same distribution as before. So now you will get a different answer, and this thing solve our contradiction with our experimental observation. So yeah, so that's why you have to include this concept of wave function collapse. So I hope you like this video. If you do, give the thumbs up, and I will see you next time.